The primary function of the inverter is to convert a DC voltage to a three-phase AC voltage for the motor. Here we are simulating the gating signals of a single phase and displaying the output waveform. Due to the circumstances, we are unable to test with the high voltage that the inverter is designed for, nor do we have a suitable motor to attach as a load. As a result, the complete filtering is not present and the output waveform is quite noisy. However, we are still able to verify that the layout of the switching stage is correct, and we can detect a roughly modulating sine wave on the output.
The power switching devices are expected to generate the greatest heat loss, so a water-cooled heatsink was designed to dissipate the heat. An iron is used to simulate the switching devices and the flow is from a tap. The test begins with the inlet at 23 degrees Celsius and the iron close to 100 degrees Celsius for 5 minutes, measuring the inlet, outlet, iron, and heatsink temperatures. The iron temperature reduced by 20 degrees and the heatsink only raised to 34 degrees Celsius, showing the heatsink's effectiveness in cooling a greater heating element to an acceptable temperature.
This hardware-in-the-loop simulation connects the inverter and a PMSM model on Simulink to test the field-oriented control loop. In this scope from the top left, we can see the torque, the synchronous current, motor speed, and three-phase current feedback that's sent to the inverter. We cycle the current set point to 100, 200, minus 200, and 100 again. We can observe that the controller reaches the correct current set point rapidly and without significant fluctuations. The speed changes proportional to the torque, and we obtain a three-phase sinusoidal current feedback. This verifies that our PI gains are properly tuned and that our field-oriented control is robust.
We are Spectre Motion, and we would like to thank you for watching our demo and for supporting the development of the Spectre X90.